In a linear regression time series model with exogenous explanatory variables and stationary data, we know that the autocorrelation will cause some problem for us. We will still have unbiased and consistent estimates using OLS, however, the OLS standard errors will be inconsistent. We know that we have two ways of dealing with this problem. One is to continue to use OLS to estimate the beta parameters, but to use robust standard errors instead of the OLS standard errors, which under mild conditions are consistent. Since the OLS estimator is no longer efficient, it's possible to derive an estimator which has a smaller variance than the OLS estimator. We sometimes call this the Gls Estimator, and that's the purpose of this lecture, to investigate how we can find efficient estimates of the beta parameter in a special case. And the special case is that we have a static time series model and the error terms follow an Ar1 process. So this is the setup of this lecture. We have a linear regression model. We have only one explanatory variable to make it simple. It's static, so I don't have any lagged x or y variables. Two of the four Gauss-Markov assumptions are satisfied. The data is stationary and the explanatory variable is exogenous. However, the error terms will be autocorrelated, and we'll assume a simple process for the error terms, namely that they follow a stationary Ar1 process, which means that epsilon t is determined by its value in the previous period plus a new error term that we call nu t. So nu t, you can think of that as the error term affecting the error term today. The expected value of each error term is 0 due to the fact that we assume that this nu t error process is white noise, and the variance of the error term will be constant as well as it's stationary. So in this case, the error terms are autocorrelated at least when rho is different from 0, but they are actually homoscedastic. So here are my two equations that describe my data generating process for y and for the error terms epsilon. So equation 1 is valid for all t, so that means that it's valid in this period but also in the previous period. So I can write equation 1 just as well as yt minus 1 is beta 1 plus beta 2 xt minus 1 plus epsilon t minus 1. This works just as well as equation 1. So let's multiply both sides of this new equation by rho. I have rho yt minus 1 rho beta 1 plus rho beta 2 xt minus 1 plus rho epsilon t minus 1. If you're wondering why I'm doing that, well, for now, no reason. Just hang on and you'll see the reason. So let's call this equation 3. It is completely equivalent to equation 1. If I have two equations and I subtract one equation from another, I get a new equation which must still be true. So let's do equation 1 minus equation 3. So on the left hand side, I do this one minus this one. So on the left hand side, I have yt minus rho yt minus 1. And on the right hand side, I do this part minus this part. So I have beta 1 plus beta 2 xt plus epsilon t minus, and let's do a parenthesis so we get the minus sign on all terms, rho beta 1 plus rho beta 2 xt minus 1 plus rho epsilon t minus 1. So let's open the parentheses and put the parameters that belong together. So we have beta 1 here and another constant here. Beta 1 minus rho beta 1, so I can write that as beta 1, 1 minus rho. We have a beta 2 xt. We have a rho beta 2 xt minus 1. Then we have the error terms, epsilon t minus rho epsilon t minus 1. So it certainly looks like I've taken something fairly simple, 1 and 2, and I messed it up completely by combining equation 1 in a weird way. The point here is if I look at equation 2, I can move rho epsilon t minus 1 onto the left hand side. Then it says epsilon t minus rho epsilon t minus 1 equal to nu t. But this part here is precisely what I have here. So I can do at least a slight simplification and write this as nu t instead. So this part is equal to this part. So let's move this second term over on the right hand side as well. Then we have the final result. Yt equal to beta 1, 1 minus rho plus beta 2 xt minus rho beta 2 xt minus 1. And then we can take this term plus rho yt minus 1 plus, then we have this term which is now nu t. We will call this the transformed model. So what have we gained from moving from the original model, this one, to the transformed model? Well, the answer is that we have a new error term. In the original model, the error term was epsilon t, which was autocorrelated. In the transformed model, the error term is nu t, which is white noise. The error terms satisfy all the Gauss-Markov conditions. Unfortunately, there is a price to pay for going to the transform model with the well-behaved errors, and that is the fact that we've made the actual model more complicated. We can see that we went actually from a static model where yt depended only on xt to this is an ADL model. You see that we have one lagged x and one lagged y, so it's an ADL 1, 1. Even worse, it's actually no longer a linear model. This is a non-linear ADL 1, 1. Due to the fact, well, the important part is here. We have a product of rho and beta 2. Notice that I can't make this trick that we sometimes do, renaming the parameters. I mean, you may think that, well, why don't I just rename this theta 1, this will be theta 2, this will be theta 3, and this will be theta 4, for example. The answer is that you can't do that in this case because we are starting with only 3 parameters. This is beta 1, by the way. Beta 1, rho, and beta 2. Those are the only 3 parameters we have. So I can't then estimate 4 parameters because out of these 4 I can't get my original 3 parameters back. And should I estimate this using OLS, then I would estimate all these theta parameters completely freely. But we have restrictions here. For example, the parameter here in front of xt minus 1 must be precisely the product of this parameter and this parameter with the minus sign. And if I estimate this with OLS, that will not happen. Fortunately, we have seen this before, and all we need to do is just to estimate this not with OLS but with NLS, nonlinear least squares. So to summarize what we have said, we instead move to the transformed model. So we calculate yt minus rho yt minus 1, and that becomes this expression to the right. Expand this, and make the replacement epsilon t minus rho epsilon t minus 1 is nu t, we get this nice nonlinear ADL model with the Gauss Markov errors. So I can just simply estimate all the parameters using NLS. So let's see how to do this in Gretel. I have data on help wanted index of ads publishing papers and the unemployment rate, and I want to estimate this model. My y variable is HWI and my x variable is UN. So all I need to do is go to model and nonlinear least squares. So this is what you need to type. We have three parameters, remember, beta 1, rho, and beta 2. So we do scalar beta 1, scalar beta 2, scalar rho, and these are initial values. NLS is a numerical procedure, so the software will have to try to go from this starting value to the value that will minimize the sum of square residuals. But since this is such a simple problem, we can just start at 0. Then we just type the equation HWI, that's my y variable, beta 1 times parenthesis 1 minus rho, that's this part over here, plus beta 2 times my x variable, which is UN, minus rho times beta 2 times lagged xt, so that's UN minus 1, plus rho times lagged y variable, so that's rho HWI minus 1. And the final thing we have to do in Gretel is to define these parameters, params beta 1, beta 2, and rho, and it will estimate all my parameters simultaneously. It will estimate my intercept and beta 2, the marginal effect of unemployment, and we now get a nice minus sign for this one, which is really what we want. The rho parameter is the parameter in the Ar1 process for the error term, and we can see that this is significantly different from 0. So we can see that the error terms are clearly autocorrelated. So these are the GLS estimates, and they are more efficient than the OLS estimates, at least assuming that the specification that we have set up for the error term is correct. Here is the same thing in eViews. In eViews we need to use C of 1 for beta 1, C of 2 for beta 2, and C of 3 for rho. So this would be C of 1 times 1 minus C of 3. That would be beta 1, 1 minus rho, and so on. This is the specification we need to do. Click OK, and then we have the same result as Gretel. I just want to quickly point out, I'm not going to dig into that right now, but eViews also has a feature for automatically estimating models where the error term follows an AR process or even more complex processes such as an AR1 process. And you can do that if you do quick estimate equation and you just write HWI constant UN, and then you can just add AR1. That will tell eViews that you want to estimate this model assuming that the error terms follows an AR1 process. Clicking OK, we get estimates. However, it is not done using nonlinear least squares, but instead a method called maximum likelihood. So the estimates will not be exactly the same. They will, however, be asymptotically the same. So this will be my estimate of the marginal effect of unemployment, and this is my rho parameter.